Yes, hello guys, welcome to the biz tutorial. Welcome to the biz tutorial, and we'll be going into introduction to pericyclic chemistry, pericyclic reaction. So we're going to talk about what we mean by pericyclic reaction. Now, basically, organic compound reaction is into three. So we have three types of organic reactions. Basically, we have the first one to be polar, the polar reaction, and the second one we have the radical reaction. We have the radical reaction, and lastly we have the pericyclic, which is where we want to discuss more on. We have the pericyclic reaction. Now, so I'm just going to explain polar reaction and radical reaction briefly, then we go straight into pericyclic reaction. When we say a polar reaction, in a polar reaction you have your nucleophile, the electron rich site, to react with your electrophile, the electron deficient species. So when you have your nucleophile reacting with your electrophile, that such reaction is said to be polar reaction. And don't forget, our nucleophile are electron rich, electrophile electron deficient. Example, maybe you have hydroxyl group. So you are reacting hydroxyl group with an alkylate, maybe like methyl bromide. So upon this reaction, the nucleophile, when there is, after sharing of electrons here, this OH will attack this carbon. You understand now? And upon attack, there will be substitution of Br. So the final product will now be CH, because CH3, because Br is a good living group. So and OH is stronger compared to Br. So you have CH3 OH plus Br. You understand now? So this example of a polar reaction where a nucleophile attack electrophile, and there will be substitution, because this is a good living group, because OH is stronger than Br. So easily OH will displace bromine. You understand now? And OH will take the place. So you have methanol and you have your bromine as a byproduct. Yes, and when we talk about radical reaction, we all know that radical are unstable species. And basically the reaction pathway for radical is three. We have the initiation to initiate, and the second, after you initiate, you have the propagation. And the last step there is the termination. You have the termination. So these are basically the three steps for radical reaction. So the three steps involved in a radical reaction. Example, you can see this in the complete chlorination of methane. The complete chlorination of methane is example. Complete chlorination of methane. And if you check the complete chlorination, it is both radical, it is a radical reaction, and also the reaction is photochemical. Yes, it is photochemical. It involves light. Now, so on this example of a radical reaction, let's take this radical CH3CH2 radical, then plus chlorine. Now chlorine gas. In this case, now there will be homolytic cleavage. Yes, homolytic cleavage, that is when bonds are shared evenly. So there will be homolytic cleavage. Now after that, what will happen is this. These two chlorine now will turn to radical also. So you have ClCl radical. And the next thing is this. The two chlorine are unstable. That's radical. Radical are unstable species. So they will tend to attack this radical. Also, one of the chlorine will attack this radical. And at the end of the day, you have you have CH3, CH2, then you have Cl. It is now stabilized due to the addition of the chlorine, then plus the remaining radical here, chlorine radical. Now, if you look at this reaction pathway, now the first thing that happens is the initiation, that is formation of radical here. That's where you initiated the reaction. So initiation involves radical formation. After the initiation, the next thing is propagation. Then the radical attack this to propagate a new product, and that's how you end the reaction. Upon propagation, the whole reaction was terminated because chlorine stabilized the initial radical given to us. You understand that? So basically, that's a radical reaction. So the where we are going to now, the pericyclic reaction, which is the main reaction we want to focus on. The pericyclic reaction occur when you have one electron. When you have one electron, in the reactant. When you have one electron in the reactant, and are reorganized, and when you have that one electron to be reorganized. So that's an example of a pericyclic reaction. It occurs when electrons in a reactant are reorganized. Do you get that now? That's pericyclic, and it is divided into 3. So the first one there is the electrocyclic. The electrocyclic reaction. The second there is the cyclo addition. The cyclo addition reaction. And lastly, the last type of reaction we have is the sigmatropic. Sigmatropic reaction. So basically, these are the 3 examples. These are the 3 types of our pericyclic reaction. So I'm going to talk about these 3 types, but it might not be in this video, as I will just briefly explain the 3 types. Then in the next video, we are going to delve into each of these types in details. Now, the first one there, the electrocyclic addition. Now, in electrocyclic addition, what you need to note is that the product of the reaction, always have, please note it is important, one fewer pi bond than the reactant. So note that is at the end of the final product. Don't forget, pericyclic involves rearrangement of one electron in the reactant. But then, so after you reorganize that one electron, when the product have one pi bond lesser than the initial material, such reaction is said to be electrocyclic. So we are going to look at one example now. Let's make use of 135 hexatriene. So this 135 hexatriene. So if you want to use this now, you have so in this reaction, So this is it. Now this, don't forget, we are under electrocyclic reaction. Now what will happen is this: this double bond will move inside. We want to try and complete the ring. You understand now? This will move in and this will come down. In the process of this one is bond formation, and the last bond here will be the one to close the ring. So upon application of your heat, so this bond formation to be precise, it is ring. Yes, ring formation. Now you are forming your ring. So don't forget, this pi bond move down here, the other one move down, and this is moving out to close, to close this region. So what will now happen is this: you now form your final product. This, you understand? Don't forget, one double bond moved in here, the other one moved down here. So this is your final product. So this is electrocyclic. That is, now if you now look at this product is now cyclo 1,3 butadiene. Hexadiene. I'm sorry, hexadiene. It is 6 carbon ring. Hexadiene. Now what I want to bring out from this is that if you look at our product, you only have 2 pi bond. You look at our reactant, we have 1, 2, 3. So meaning that the number of pi bond in the product is lesser than that of the reaction. This is electrocyclic reaction. So that's it. Then let's move to the second reaction type, the cyclo addition. The cyclo addition. Now the cyclo addition reaction. In the cyclo addition reaction, here the product has 2 fewer pi bond lesser. The product has 2. In the case of electrocyclic, it was 1. So you have 2 fewer pi bond. You have 2 fewer pi bond than the reactant. So don't forget. So that is cyclo addition. So we are going to work with this now. So now let's make use of this example. Just take a look at this. You have this. So plus 18. So they are double bond. That's 18. So we have to react the two together now. Now upon reacting, now this will move down. You understand now? This will move down. Then this one, this single 18. When this one move down, you have a closure here. Then you have 2 18. One will now come here, one of the 18, and the remaining one will be the one to close this bond at the top. You understand? So the only bond that will exist is this bond. Do you understand now? So at the end of the day, this is what you have. So you have a 2 sigma bond formed. So this is what you have. That is, here you have 2 pi bond plus another pi bond to give you 2 sigma bond. You understand now? So you have a sigma bond here, and you also have another sigma bond here. So what am I trying to say in essence? From here, this bond comes down to close this ring, and this pi bond closes this region, and the remaining bond here closes the ring to form this beautiful structure with 2 lesser pi bond compared to electrocyclic. So let's talk about the last one, which is the sigmatrophic. Sigmatrophic rearrangement. So we are talking about the sigmatrophic rearrangement, and here under sigmatrophic, the product and reactant both the product and reactant have the same pi bond number. They have the same number of pi bond. Do you get that now? So that's the difference between the three. The first one has one lesser pi bond for the product, the second has two lesser, and here you have the same number for sigmatrophic. Now example, now let's make use of this beautiful compound. So you have this. Now what will happen? Basically, there should be chances of closing the bond. Then what will happen is this double bond remove in, you understand, and then this we want to close this ring. Automatically, if this double bond is coming down and this is coming up, definitely this double bond will need to stabilize, this single bond will stabilize this region. You understand now? Look at the bond movement. The first one, this double bond will come in, this one will come in, and here this one will move out, and this is going up. Basically it's because this sigma bond is moving up. That is the reason why this double bond is coming in to balance, to stabilize the region. So what I'm trying to say is that the reaction is at equilibrium. You can move from product to reactant, just make, because you are applying your heat now. Now look at this is what you now have as your final product. So from your final product, I will explain again. Then you have this. Do you get it now? So these are products. Now if you look at it now, this here initially we had a double bond here, you understand, and the double bond moved in and you have it here, you understand. Now this single bond moved up, that's why this region becomes opened, and the double bond here closes this rear, that's why you have this region enclosed. Do you get it now? So that's the pi movement. And if you look at it, you have one pi bond here, another pi bond here, that's 2 pi. And if you look at this, you have 1 pi, another pi, that's also 2 pi. So basically you have the same number of pi electron. So this is example of sigmatrophic